The nearest Earth? Or our nearest cosmic graveyard? If we ever build a starship and leave the solar system for the very first time, will our destination already be dead? Because the most obvious target for humanity's first interstellar journey is not some distant, exotic galaxy. It is Proxima Centauri b, our nearest potentially Earth-like planet, and it might not be a second Earth at all. It might be a warning label on the universe. In the hunt for alien life, proximity matters. A world only 4.24 light-years away is, on cosmic scales, right next door. So when astronomers announced Proxima Centauri b in 2016, orbiting the closest star to the Sun, it felt like the script had already been written. Rocky planet. Similar energy from its star as Earth gets from the Sun. Right in the so-called Goldilocks zone. Optimistically speaking, this was our best interstellar backup plan. But while the headlines called it Earth 2.0, the universe may have had other ideas. Proxima Centauri is a small, dim red dwarf, but it is anything but calm. It blasts its planets with intense flares, X-rays, and ultraviolet radiation. This means that the same star that makes Proxima be technically habitable on paper might also be trying to tear its atmosphere away, particle by particle. So here's the existential question we have to face. Does it matter that a planet sits in the habitable zone if its own star is constantly trying to turn it into a cosmic desert? If Proxima b has already lost its atmosphere and its water, how many other habitable worlds in the galaxy are just sterile rocks hiding behind hopeful labels? It should be noted that we do not yet know which way Proxima b is gone. There are two stark possibilities. In one future, it is a harsh but habitable frontier world, tidally locked, with one side an endless day and one an endless night, yet with a surviving atmosphere that shuttles heat around and keeps liquid water clinging on. A place we could, in principle, visit. In the other future, it is a cosmic graveyard, a stripped, frozen, or scorched surface, its air blasted into space by billions of years of flares. No oceans, no clouds, maybe not even a trace of past life. If that is the truth, Proxima b forces us to rethink our entire strategy for where to search and where to send our first starships. So, let's begin. By the end of this video, we will see what the data actually tell us about Proxima Centauri b, how brutal its environment may be, and whether this nearby world is a stepping stone to the stars, or our nearest cosmic dead end. So it's time to find out the truth. Why Proxima b matters, our first real test of the habitable zone idea. If we want to know whether the habitable zone really means habitable, there is no better test case than Proxima Centauri b. In the hunt for alien life, this one planet has become a kind of cosmic exam paper for everything astronomers have been assuming for decades. For a long time, the strategy sounded simple. Find an Earth-like planet in the Goldilocks zone of its star where liquid water could exist, and you have a decent place to start. We found thousands of candidates scattered across the galaxy, but they were all so far away that they felt abstract, like dots in a catalog, rather than destinations. Proxima b is different. At just over 4 light-years, it sits close enough that, in principle, we can imagine future probes, even starships, actually going there. This means our nearest neighbor is also our first realistic laboratory for testing whether the Goldilocks zone idea really works. And there is something else. Red dwarf stars like Proxima are not rare exceptions, they are the rule. They are the most common type of star in the Milky Way, and billions of them could host small rocky planets in tight orbits. If planets like Proxima b, bathing in the right average energy but under harsh radiation, turn out to be mostly dead, then the number of truly life-friendly worlds drops dramatically compared to our most optimistic estimates. Optimistically speaking, a thriving biosphere around a red dwarf would multiply the places life could exist. But while that sounds exciting, the opposite result would be a serious warning sign about our assumptions. The difficulty is that we are trying to judge all of this with very limited data. We cannot see Proxima b's surface directly. We have not yet confirmed that it even has an atmosphere, let alone what that atmosphere is made of. Instead, we are reconstructing billions of years of violent stellar history from tiny changes in starlight, from X-ray and ultraviolet measurements, and from computer models that we are still testing on our own solar system. It should be noted that even small changes in those models can flip Proxima b from marginally habitable ocean world to long desiccated rock, so it's time to find out the truth about how fragile this kind of world might be. Proxima Centauri itself makes the question impossible to ignore. It is not just any red dwarf, it is the closest star, part of a triple star system with Alpha Centauri A and B, and it hosts at least 3 planets that we know of. Proxima C is a colder, more distant super-Earth. Candidate D hugs the star in a scorching inner orbit, but Proxima B sits right in that Goldilocks zone, receiving a similar overall energy flux to Earth. If any planet around Proxima can hold on to liquid water, it should be this one. So which is it? Did we get incredibly lucky with our nearest neighbor turning out to be truly habitable, or incredibly unlucky with our closest Earth becoming the perfect example of how the habitable zone can lie to us? Meet Proxima Centauri B, the planet that looked too good to be true. To answer that, we need to meet the suspect up close. Proxima Centauri B is not just any distant exoplanet on a telescope slide. It is the innermost known planet of the closest star to the Sun, Proxima Centauri, discovered in 2016 by watching the star wobble ever so slightly in space. That wobble is crucial. Astronomers used the radial velocity method, tracking tiny shifts in the star's light as Proxima B tugs on it during each orbit. Every 11.2 days, like clockwork, the planet swings once around its red dwarf host. A year there would pass in less than 2 weeks for us. In the hunt for alien life, that kind of regular, measurable signal is a dream because it lets us pin down the planet's basic properties with surprising precision. So, let's begin with the numbers that made everyone sit up. From the strength of that tug, we infer a minimum mass of about 1.3 times Earth's. Minimum mass means we only know the lowest possible value because we do not yet know the exact tilt of the orbit relative to our line of sight. If the orbit is not perfectly edging, the true mass could be higher. But even if we push it upward reasonably, we are still in the realm of a small, dense world, not a bloated gas giant. This means Proxima B is almost certainly rocky. Its mass is far below typical mini-Neptunes, and it hugs its star at only about 0.05 astronomical units, 20 times closer than Earth is to the Sun. At that distance, an extended hydrogenic envelope would be extremely hard to keep. The star's radiation and winds would strip it away. It should be noted that this close-in, low-mass combination is exactly what we expect for a terrestrial, Earth-like planet. And yet, despite being so close, the average energy it receives from its star is roughly similar to what Earth gets from the Sun. Proxima is a cool faint red dwarf, so its Goldilocks zone is tucked right up against it. Proxima B sits squarely in that habitable band, where liquid water could exist on a surface, at least in principle. Optimistically speaking, this was the headline: a nearby, roughly Earth mass world in the habitable zone of the nearest star. Then there is the distance, just over 4 light-years. On galactic scales, that is next door. Proxima B is orders of magnitude closer than most exoplanets we study, making it a prime target for future giant telescopes and, in the more adventurous timelines, the first true interstellar probes. If we ever send hardware to another star system, how could we not aim for this one? But while the orbit and mass looked almost ideal, there was a catch written into the discovery from day one. Proxima Centauri is an active, red dwarf, prone to powerful flares and intense high-energy radiation. Close orbit plus violent star, is that a recipe for a thriving atmosphere or for a stripped, dead surface? So it's time to find out the truth about what that environment actually does to a planet like Proxima B. New eyes on our neighbor. How next-gen telescopes will judge Proxima B. To answer that, we need new eyes. Because at this point, arguments on paper are not enough. In the hunt for alien life, there comes a moment when theory has to face the sky, and for Proxima B, that moment is arriving right now. Enter the James Webb Space Telescope and its successors. JWST is essentially truth serum for distant planets, a space observatory with ultra-sensitive infrared vision built to peel faint planetary signals out of the glare of their host star. On the ground, giants like the extremely large telescope in Chile will use huge mirrors and advanced optics to do the same, separating a dim Earth-like world from a blinding red dwarf only a fraction of a pixel away. So, let's begin to see how they will judge our neighbor. We have already seen what JWST can do with systems like TRAPPIST-1. By watching those planets cross in front of their star, it measures tiny dips in light and even sniffs starlight filtered through their atmospheres. This means we can tell when a planet is effectively airless or when a thick blanket of gas is present. But while TRAPPIST-1's worlds cooperate by transiting, Proxima B does not. It never passes neatly across its star from our point of view, so JWST has to work much harder and rely on indirect methods. So, What can we do instead? One approach is to follow Proxima b through its entire orbit and measure how the combined light of star plus planet changes with phase. A bare rock, with no atmosphere to move heat around, should blaze on the day side and plunge toward darkness on the night side, producing a strong thermal contrast. It should be noted that if J West or the ELT see a smoother, more even signal, that would hint at something redistributing heat, a substantial atmosphere, maybe even oceans or clouds. Future high-contrast imaging will push this even further, trying to directly separate Proxima b's faint glow from its star. In principle, that could reveal reflected starlight, cloud patterns, or at least confirm whether the planet is wrapped in a thick, protective atmosphere, or stripped almost bare. So it's time to find out the truth. Will the data show a temperate, moderated world in the Goldilocks zone, or a cosmic warning sign, with a scorched day side and a frozen night side? Optimistically speaking, we are standing right at the edge of being able to say whether the closest potentially habitable planet is alive or dead. And the same tools that have already delivered bad news for some TRAPPIST-1 planets are now turning their gaze toward Proxima Centauri b, our nearest test of whether such worlds are destinations for life or dead ends in the wider universe. Two futures for Proxima b: frontier world or sterilized rock. So what are the actual options for Proxima Centauri b? Because, in the hunt for alien life, this planet is either our most exciting neighbor or our closest disappointment. Optimistically speaking, imagine the best case version first. Proxima b managed to hold on to a thick atmosphere, maybe even denser than Earth's. Under the glare of its red dwarf star, the day side bakes in constant light, but powerful winds grab that heat and drag it around the planet. Instead of a scorched hemisphere and a frozen one, you get a dynamic, circulating climate. In that scenario, the most comfortable place is not the day side or the night side, but the thin ring in between, a permanent twilight zone wrapped all the way around the planet. Here, temperatures could hover in the Goldilocks zone for liquid water. Oceans or seas might hug this band, with clouds streaming overhead and ice creeping into the darkness. It should be noted that climate models suggest exactly this kind of eyeball Earth is possible if the atmosphere is thick enough and contains greenhouse gases. If that is real, Proxima b is not just habitable on paper. It becomes a proof of concept that red dwarf systems can host stable, Earth-like environments, even under tidal locking. This means the most common type of star in the galaxy could also be the most common cradle for life. But there is a very different future on the table. Proxima is not a quiet star. It blasts its planets with X-rays and ultraviolet light, plus fierce stellar winds. Over billions of years, those flares can erode an atmosphere, molecule by molecule, especially on a planet that orbits once every 11 days, pressed right up against its star's magnetic storms. In that pessimistic scenario, whatever ocean Proxima b started with is boiled off and broken apart by radiation. Hydrogen escapes to space. The atmosphere thins, then vanishes. The surface is left as a desiccated, airless rock, more like a burnt-out Mercury than a second Earth. Maybe, deep underground, pockets of water and chemistry survive as tiny refuges, but from orbit, it would look dead. So which is it? Frontier world, with a twilight ring of seas and maybe life, or sterilized rock, our nearest cosmic graveyard? That binary choice is not just about one planet. Either Proxima b shows that habitable zones around active red dwarfs can truly be habitable, or it becomes a cautionary tale that the label is dangerously misleading. So it's time to find out the truth. To do that, we have to stop looking only at the planet and start asking a much harder question. What kind of star is Proxima Centauri really, and what is it doing to its closest world? Who's talking to you, and where this journey is going? So, if Proxima b might be either a second Earth or a cosmic warning sign, who is actually taking you through this? And this is where we build a kind of interstellar shortlist. In the hunt for alien life and future exploration, we have been moving system by system, asking a simple but ruthless question: which nearby worlds are truly worth our effort, and which are beautiful dead ends? So, let's begin by laying out where we are heading in this episode, because this is not just a random tour of a famous exoplanet. First, we are going to step back and look at Proxima Centauri itself. What does it mean that our closest stellar neighbor is a small, cool red dwarf that can unleash flares hundreds of times more energetic than anything our sun produces? We will see why these stars are both incredibly promising and incredibly dangerous for any planet trapped in their Goldilocks zone. Then, we will rewind the clock on Proxima b. We will ask what this planet might have started with: a thick atmosphere or almost none, a global ocean or just scattered seas. We will follow the radiation, the stellar wind, and the tidal forces as they strip, bake, or possibly protect different regions of the surface. This means we will be treating Proxima b as a character with a life story. not just as a set of orbital numbers. After that, we will compare this world to other red dwarf systems we have already met, especially TRAPPIST-1. JEST is now giving us hard data on whether those planets still have atmospheres at all. It should be noted that some of the early results are not encouraging. By putting Proxima b side by side with TRAPPIST-1 and its siblings, we can see whether it is an outlier or part of a larger, troubling pattern. Finally, we will zoom back out and ask what all of this means for our interstellar priorities. If humanity could send just one robotic probe in the next few centuries, should we fire it straight at our nearest neighbor, or skip Proxima entirely and target a calmer, more distant star instead? Optimistically speaking, there might be a surprising answer. Quick pattern interrupt. Imagine you are on the mission planning committee at the end of this video. You will have to cast a vote. Proxima b, with all its drama, or a quieter, sun-like star farther away? Stay with us to the end, because we will walk through that thought experiment together, using everything we have learned from Proxima's past and present to decide whether this world deserves humanity's first real interstellar ticket. Red Dwarfs 101. Why the smallest stars cause the biggest headaches to cast that vote. We first have to understand the kind of star Proxima actually is, because the moment we say red dwarf, we are stepping into a very different universe from our comfortable sun. So, let's begin with the basics. Red dwarfs are small, cool, low-mass stars, roughly a tenth to a little over half the mass of the sun. They sip their hydrogen instead of gulping it, burning fuel so slowly that they can live not just billions, but trillions of years. In the hunt for alien life, that sounds perfect, right? A star that stays on for almost forever, giving a planet endless time to evolve. But while long lifetimes are a huge advantage, the low brightness of a red dwarf creates an immediate headache. Because these stars are so dim, their Goldilocks zone is pulled in very close. This means a planet has to orbit in just a few days or weeks to receive Earth-like energy. Proxima b, for example, loops around its star in just 11 days. At those distances, tidal forces are intense, and tidal locking becomes extremely likely, with one side of the planet in permanent day, and the other in endless night. What does that do to habitability? A tidally locked world can still be habitable, in theory, with a thick enough atmosphere or ocean to move heat around. But the climate is pushed to extremes, a blazing substellar point under the eternal noon, a frozen nightside where air and water might collapse as ice. The entire question becomes, can the atmosphere survive long enough and stay thick enough to smooth those extremes out? Here is where red dwarfs reveal their biggest problem: stellar activity. Young and even middle-aged red dwarfs can unleash powerful flares, intense X-ray and ultraviolet radiation, and strong stellar winds. It should be noted that for a Closian planet, this is not a distant light show. This is a constant particle sandblaster, directly attacking the upper atmosphere and stripping it away over time. So it's time to find out the truth about priorities. We often focus on whether a planet is Earth-like in mass, size, and composition, but an almost perfect Earth mass world, with liquid water at the start, can be rendered completely uninhabitable if its host star is too violent, for too long, at too close an orbit. The star's behavior is not background scenery, it is a main character in the story of life. Optimistically speaking, a quiet red dwarf could still nurture a stable, habitable system for eons, but Proxima Centauri is not quiet. So what happens when we place Proxima b right in the line of fire of one of the most active nearby red dwarfs we know? In the next section, we will follow that radiation, flare by flare, and see what it might already have done to Proxima b's atmosphere. Inside Proxima Centauri, the star that won't stop flaring, so if Proxima b is standing in the line of fire, what kind of star is pulling the trigger? To answer that, we have to step inside Proxima Centauri itself, because this small, red dwarf controls almost everything about whether its planet can be habitable. Proxima Centauri is tiny by stellar standards. It has about 12% the mass of the Sun, and only around 14% of the Sun's radius. If you could place it next to Jupiter, it would look only slightly larger in size, yet it is still a true star, fusing hydrogen in its core. But while it is small, it is also faint. It emits less than 1% of the Sun's luminosity. This means that its Goldilocks zone is pulled inwards to a scorchingly close distance. Proxima b orbits well inside Mercury's orbit would be in our solar system, circling its star every 11.2 days. In the hunt for alien life, a tight orbit around a cool red dwarf sounds efficient. You get Earth-like average energy from a much dimmer star. But while the numbers look promising on paper, the reality of Proxima's activity changes everything. Proxima Centauri is a classic flare star. Observations show frequent eruptions that can double or even triple its brightness for minutes to hours. Occasionally, it unleashes superflares that dwarf anything the sun has produced in recorded history, blasting out intense X-ray and ultraviolet radiation. It should be noted that Proxima b is sitting right in this storm, so close that each major flare is like a blowtorch passing across its sky. When we quantify this, the picture becomes even harsher. Proxima b likely receives tens to hundreds of times more X-ray flux than Earth does. The stellar wind, a stream of charged particles from the star, may be hundreds or thousands of times stronger than the solar wind at Earth's orbit. This combination is extremely efficient at stripping away an atmosphere, molecule by molecule, especially from an Earth-like planet that has to huddle so close just to stay warm. Then there is the question of rotation and magnetism. At such a close distance, Proxima b is almost certainly tidally locked, with one permanent day side staring at the star and one eternal night side turned away. So, let's begin to imagine that climate, a blazing hemisphere under constant radiation, and a frozen hemisphere in endless darkness. Can a magnetic field survive under those conditions? Some models suggest the planet's interior could still generate a field, but its shape and strength might be very different from Earth's, leaving large regions exposed. So it's time to find out the truth. In a system this brutal, is there any realistic way Proxima b could have held on to its atmosphere and water for billions of years? Or are we already looking at a world that was doomed from the start? Rewinding the tape, could Proxima b ever have been Earth-like? To answer that, we have to do something strange. We have to rewind the tape of Proxima b's history, back to when this world and its star were young and far more dangerous than they are today. Young red dwarfs are not gentle parents. Proxima Centauri, already an active star now, would have been even more extreme in its youth, throwing out powerful flares, intense rays, and thick streams of charged particles. All of that would have slammed into a young Proxima b right when its atmosphere was still forming, and right when any oceans would have been most vulnerable. In the hunt for alien life, this early phase can make or break a planet before life ever has a chance to start. So, let's begin with how Proxima b might have formed. One scenario is that it started out wrapped in a deep blanket of hydrogen and helium, a mini Neptune close to the Goldilocks zone. Another is that it assembled farther from the star, rich in ice, and migrated inward, becoming a compact ocean world with several times Earth's water. It should be noted that both options are very different from Earth's drier, rock-dominated beginnings, and they strongly change how well a planet can hang on to its atmosphere under stress. How does this compare to our own story? Early Earth also faced a more active sun, with higher ultraviolet output and more frequent eruptions, yet Earth kept its air and oceans. Our magnetic field helped deflect the solar wind, volcanic outgassing continuously resupplied the atmosphere, and our greater distance from the star reduced the worst radiation. Proxima b, by contrast, orbits in just 11 days, bathing in far stronger high-energy radiation. It had to play the same survival game, but on hard mode. So what do the models say when we run this story forward? Many simulations suggest that if Proxima b only had an Earth-like atmosphere and Earth-like oceans, the star's activity could strip them away in a few hundred million to a couple of billion years. This means that unless it began with an enormous reservoir of water or with a very thick atmosphere that could be gradually eroded, it may have dried out long before complex chemistry could organize into life. But here is the pattern interrupt. Instead of asking, is Proxima b habitable now? We have to ask, did it ever get a real chance? Was this planet born already behind the habitability curve compared to Earth, its fate sealed by its formation and its vicious stellar environment? Optimistically speaking, there is still one more twist we have to consider. Even a battered world can sometimes adapt. So what would Proxima b look like if it survived, but was reshaped into something very different from Earth? Strange days and eternal nights. Climate on a tidally locked world, so if Proxima b survived the worst of its star's fury, what kind of world did it become? Did it end up as a place with familiar blue skies and seasons, or something far stranger, locked into a pattern of strange days and eternal nights? Because around a small red dwarf, like Proxima Centauri, tidal forces do something dramatic. Over time, they grab hold of a planet and slow its spin until one hemisphere always faces the star. This means Proxima b is very likely tidally locked. One side would sit under a permanent, unmoving sun blazing down from the same spot in the sky. The other side would be buried in endless night, a frozen hemisphere that never sees dawn. Between them, there is a narrow ring where the star would hover forever on the horizon, a band of eternal sunset. At first glance, that sounds hopeless for anything habitable. A scorched day side, an airless cryogenic night side, and only a razor-thin twilight strip where liquid water might cling on. But while that picture is simple, it should be noted that real climates are not. If Proxima b kept a reasonably thick atmosphere, the story changes completely. With enough air, winds can pick up the dayside surplus heat and carry it around the planet. Hot gas rises under the substellar point, flows toward the dark hemisphere, cools, sinks, and returns. In the hunt for alien life, this kind of global heat engine is crucial. Climate models of Proxima b, like planets, show that with even a modest atmosphere, temperatures begin to smooth out. Instead of a single habitable line, you can get a broad, warm region spanning much of the dayside hemisphere, and a night side that is cold, but not utterly frozen solid. So what do simulations actually say? When researchers feed Proxima's radiation, the planet's orbit, and different atmospheric pressures into their models, a pattern emerges. With Earth-like or slightly denser atmospheres, stable liquid water can exist under the perpetual noon of the substellar point, or stretched around into the twilight ring. With thinner air, the contrast sharpens. The night side cools so much that gases start to freeze out onto the surface. This means the atmosphere can literally collapse into ice, leaving the planet air-starved and hostile. More exotic possibilities appear as well. One scenario gives Proxima b a deep global ocean. The night side freezes into a continent of ice, but liquid water survives below, circulating slowly back toward the light. Another has a thick carbon dioxide atmosphere, trapping heat like a supercharged greenhouse. That world might stay warm enough for oceans, yet shrouded in dense clouds and high pressures, perhaps friendly only to hardy microbes. So it's time to find out the truth. All of these climates depend on a single unknown. Does Proxima b still have an atmosphere at all? Or are we sketching weather maps on a bare rock, circling our nearest star in naked vacuum? What the data whisper, atmosphere or airless rock? So if everything depends on the air above Proxima b, what does the universe actually let us see? Right now, frustratingly, not very much. Unlike the TRAPPIST-1 planets, Proxima b does not pass directly in front of its star from our point of view. That single geometric detail blocks one of our best tools. We cannot simply let the James Webb Space Telescope watch starlight filter through an atmosphere and read off the gases like a barcode. Instead, we are working with shadows of evidence, radial velocity wobbles, the star's violent mood swings in X-ray and ultraviolet light, and a few tentative phase curve hints of how bright the planet's dayside might be. So, what can we infer from this incomplete picture? Proxima Centauri is an active red dwarf, and it bathes its close-in planet in X-ray and UV radiation hundreds of times stronger than what Earth receives. Models of atmospheric escape tell us that under this kind of assault, a thin, Earth-like atmosphere is vulnerable. Over billions of years, energetic particles and flares can strip away air and water, molecule by molecule, especially on a world that may be tidally locked and constantly facing its star. This means a normal modern Earth scenario is, in many simulations, the first casualty. But while theory leans toward loss, there is still room for thicker, more stubborn envelopes of gas. A dense CO atmosphere, or one continually replenished by volcanic outgassing, could survive much longer. It should be noted that some climate models even allow a steam-rich or high-pressure ocean world where the surface is harsh but pockets of liquid water might persist below clouds or ice. Here is where TRAPPIST-1 quietly joins the jury. In the hunt for alien life, that system is our best laboratory for red dwarf planets. JOEST has already looked at several of its inner worlds. TRAPPIST-1b and 1c appear effectively airless or with only extremely thin CO. No thick, puffy atmospheres there. Even TRAPPIST-1, in the middle of its Goldilocks zone, has had a primordial hydrogen blanket and a Venus-style CO shroud ruled out. Optimistically speaking, some more subtle atmospheres remain possible, but the pattern is sobering. Close and rocky planets around small stars may commonly lose their air. Yet, the story is not closed. A strong magnetic field could have shielded Proxima b's upper atmosphere from the worst of the stellar wind. An initially water-rich composition, perhaps with deep global oceans, might have provided a huge reservoir of material to lose while still leaving some behind. Continuous volcanic activity could act like a planetary life support machine, belching out CO and other gases as fast as the star strips them away. So, let's begin to weigh the odds. The data whisper that Proxima b is likely stripped or heavily battered, more scarred survivor than pristine Earth twin. But does that make it a dead end for life and for our interstellar ambitions? Or, paradoxically, the most important first destination we could choose? Dead end or first step? Rethinking our red dwarf strategy. So, if Proxima b, our closest habitable zone neighbor, looks more like a scarred survivor than an Earth twin, what does that actually tell us about the rest of the galaxy? In the hunt for alien life, this single planet suddenly becomes a case study with huge consequences. Proxima Centauri is not special. It should be noted that it is a fairly typical red dwarf, small, cool, and violently active when it flares. This means that if our nearest Goldilocks zone planet has probably lost much of its atmosphere, then billions of similar worlds, hugging billions of similar stars, might be facing the same slow erosion. We are not just asking whether one planet is habitable, we are asking whether an entire class of easy targets might be mostly dead ends. But while red dwarfs may be dangerous, they are incredibly tempting. They dominate the Milky Way. Most stars in our local neighborhood are exactly this kind of object. Their habitable zones are close in, so planets like Proxima b, or the TRAPPIST-1 system, tug on their stars more strongly and cross their disks more often. That makes them far easier to detect and study with current telescopes. Optimistically speaking, if any atmospheres survive there, we could be the first generation to read them. Yet the very proximity that helps our telescopes also exposes those worlds to intense X-ray and ultraviolet radiation. The convenience may come with a fatal bias. So here's the strategic dilemma. Do we keep pouring our attention into red dwarf systems because the data are rich, even if most of the planets turn out to be airless, waterless rocks? Or are we quietly overinvesting in the wrong neighborhood of the universe just because it is the brightest one in our instruments right now? So it's time to find out the truth about where we aim next. Pattern interrupt. Imagine you are sitting on a future mission planning committee, and you have funding for exactly one interstellar probe. On the table are two targets. First, Proxima b, only 4.2 light-years away, but quite possibly stripped, tidally locked, and marginally habitable at best. Second, a more distant world around a calm K-dwarf or sun-like star, with a wider, quieter Goldilocks zone and a long history of gentle radiation, but perhaps 15 or 20 light-years away. Which planet do you choose? The risky neighbor, or the promising stranger? The nuanced answer is that Proxima b might be a dead end for life as we know it, yet scientifically, it is the opposite of a dead end. By confronting us with the harsh reality of red dwarf environments, it forces us to recalibrate our search strategy, to weigh quiet stars more seriously, and to design the next generation of telescopes and probes with these hard lessons in mind. So, is Proxima Centauri a dead end? Or just a harsh teacher in the hunt for alien life? We have spent this whole journey balancing hope against some very unforgiving physics, so it's time to find out the truth as honestly as we can. On the hopeful side, Proxima b is still one of the most tempting worlds in the sky. It has a roughly Earth-like mass. It orbits within the Goldilocks zone of the closest star to the Sun, and on average it receives a similar amount of energy to Earth. If you only looked at those numbers, you might sketch blue oceans, white clouds, and continents lit by a red dwarf sunrise. That was the dream when it was first announced. But while the orbit and the mass are encouraging, the environment around this planet is anything but gentle. Proxima Centauri is a flaring red dwarf, blasting its system with X-rays and ultraviolet radiation hundreds of times stronger than what Earth receives. Over billions of years, that means intense stellar winds, atmospheric escape, and a constant threat of stripping away surface water. Add likely tidal locking, with one side an endless day and the other an endless night, and you have a climate that must fight for every stable patch of liquid water. The sobering lesson from TRAPPIST-1 only sharpens this picture. There, JWST is already telling us that the inner planets almost certainly lost their atmospheres, and even worlds in the habitable zone show no easy, Earth-like signatures. It should be noted that TRAPPIST-1 is actually quieter than Proxima Centauri. This means Proxima b has probably faced an even harsher evolutionary path. So where does that leave us? Given current data and models, the probabilistic verdict is not comforting. Proxima b is more likely than not to have lost a large fraction of any Earth-like atmosphere and surface oceans it started with. Optimistically speaking, it might cling to a marginally habitable region, perhaps a terminator ring of liquid water, or sheltered basins under a dense, CO2-rich sky. Pessimistically, it could be a mostly sterile rock, with only thin, residual gases and frozen or boiled away water. In that sense, dead end does not mean scientifically useless. It means Proxima b is probably not a lush second Earth waiting for us, and it may not be the best first target for a crude interstellar mission or for complex, surface-dwelling life. Yet it remains a perfect natural laboratory for understanding how red dwarf planets live or die. and there is still room for surprises. Exotic scenarios involving powerful magnetic fields, thick atmospheres, or even subsurface oceans could preserve hidden niches. Upcoming observatories like JWST, the Extremely Large Telescope, and the Habitable Worlds Observatory will test these ideas directly. Whether you see Proxima b as a warning or a waypoint, the next decade of observations will either rescue it from the dead end category or confirm that our nearest neighbor is a beautiful, silent tomb, and that is exactly why what we do next matters. Your turn. Would you still go to Proxima b? So now it comes down to you. If, in the next few centuries, humanity could only launch one true interstellar probe, where would you send it? Do we aim straight at Proxima Centauri b, this harsh, possibly airless world right on our doorstep? Or do we skip our flawed neighbor and hold out for a more distant, calmer star, with a truly promising blue planet in the Goldilocks zone? In the hunt for alien life, that choice is not just technical, it is philosophical. Proxima b might be a beautiful, silent tomb, stripped by its violent red dwarf of atmosphere and oceans. But while it may be a dead end for life as we know it, it is also the closest real test of everything we think we understand about habitable, Earth-like worlds around small stars. So, let's begin with you. Tell us in the comments, are you team nearest first, science no matter what, or team wait for a world that actually looks alive? Would you vote to send that one priceless probe to Proxima b, to read its scarred rocks and broken sky up close? Or would you spend those centuries of effort on a quieter system, perhaps around Tau Ceti or Teegarden's star? Which piece of data from this video pushed you one way or the other? It should be noted that there is no purely safe answer here. Choosing Proxima b means accepting that we might spend our first interstellar mission on a planetary autopsy. Skipping it means we could ignore the nearest warning sign in the entire universe about what red dwarf habitability really looks like. This means your reasoning matters. Explain it. Argue with each other. Which risks would you take? If you want more deep dives into specific planets like this, from Proxima b to the TRAPPIST-1 system, tap like so we know to keep going. And if you want to follow what JEST and the next generation of telescopes are quietly revealing, subscribe, because we are just getting started. In upcoming episodes, we will unpack the latest JEST results on the TRAPPIST-1 planets, especially TRAPPIST-1e, and ask whether any of them truly beat Proxima b as homes for life. We will look at nearby systems such as Tau Ceti and Teegarden's star, and then rank the top real candidates for life in our stellar neighborhood based on the best data we have. Optimistically speaking, Proxima b has already done something profound. It forced us to confront the possibility that many habitable zone planets are anything but, and to get smarter about where we look for our cosmic neighbors. The real question now is simple, and yet enormous. When we finally send that first probe beyond the sun's light, will it be heading for a dead world, or the first place we truly expect to find life? The answer to that will shape everything that comes next.